So when we left off, we had just talked about the relocations, right? And we'd said the whole point of the relocations is it's just a big list of every single place you must change in the file if the module gets moved around in memory. So here we were looking at ACL edit.dll, and this just says if the OS loader decides to move ACL edit.dll in memory, go ahead and, add the delta between where it expected to be and where it will actually be. Add that to all the RVAs, which are specified by, one of these start virtual addresses plus the offset, which is given by the bottom 12 bits of each of these things immediately after it. And so that's just basically saying all the places you need to change. And so that means for memory integrity checking purposes, that the stuff in memory will anytime it gets moved around, it'll be different. So for executables, like I said, on non-ALSR systems, they're probably not going to be relocated, and therefore they're going to be what you expect. DLLs, they may or may not be, and kernel modules, since I said OS loader doesn't even care, it just loads them wherever, those are almost certainly going to have relocations applied. So now we'll start talking, this is just a quick little overview about threads, and then we're going to talk about thread local storage. So we've already seen a couple of times already. A second. What's this? Oh, it's cache. We've already seen a couple of times those indications that the OS has, multiple different virtual address spaces for different processes. Previously, we had on the board that, this is task manager space, this is calc.exe space. In that other slide deck from the intermediate x86 class, we saw that, the OS can have mapped to, two different processes. They can have different virtual memory spaces, and they're mapped to the same physical address space, right? So the thing to understand here is that this may be one process's address space, and this may be one process's address space. But in OS's, we have the notion of threads, and a thread is different information about running subcomponents of a given process. One way to say it. So we can have a single process, and if it's single-threaded, it means that there's only one control flow bit. There's only one bit of information about control flow that says we start executing the code starting at address of entry point, and it just keeps executing the next instruction, gets to a jump, it jumps to there, gets to a call, calls to there. But it's still all one thread within a single process. So it's all just one thing. So we can have multiple threads within the same process, which can be executing at completely different areas. So there the point is, it's still the OS's job to, within a single process address space, keep metadata about, I will pretend that there's this notion of a thread, and I'll say this thread is currently stopped at EIP equals to whatever. And then I'll have this other thread, which is currently stopped at EIP equals whatever. And the OS basically swaps those in and out, and it says, okay, here were all the registers when that thread stopped. I'm going to start it up, and I'm going to load up the registers with all those stored values, load up the EIP with the stored value, and I'll let that run for a little while. And I'll let that run until it either says, okay, I'm waiting on something, at which point it can yield, and it'll say, okay, OS, go ahead and run some other thread. Or eventually, if it just times out, if it runs for a certain amount of time, the OS can say, okay, thread, you've ran for long enough. I'm going to run another thread. And it saves off all the state about wherever the thread is right now, whatever the registers are, saves it off, grabs a different thread, pulls it in, and loads it up, lets it run for a while. And it's basically the exact same notion as exists with the fact that the OS is swapping around between different processes, right? So the OS is responsible for taking process A and process B, and it says, okay, process A, you can run for however long you want to run, but eventually I'm going to cut you off and say, no, you've run long enough. It's process B's time. And so the whole point is the OS is responsible for context switching between different processes, and within a process there can be an individual thread, each of which has its own metadata about where it's executing, what sort of things it has. But the important point here is that different processes, the OS keeps different address spaces. So we've said repeatedly that, if I make a change to one process, if I inject a DLL into process A, that does not in any way affect process B. right? So each of the processes has separate memory spaces. Now with threads, each of them is running within the context of a single process address space. So two different threads can see the same memory within this guy's process address space, but the thread over here can't see anything about the thread over there. So threads run within a single virtual memory space for a single process, and processes each have their own separate virtual memory spaces. So that's the setup to start talking about thread local storage. So there's this notion of thread local storage, which is basically just saying, well, normally a thread can, two threads will all see the exact same data, in the same process address space. If they read the same virtual addresses, they'll see the same data. It may be desirable in some cases to say, I want some data which only this thread can see, and I want some data which only that thread can see. And that's what's called thread local storage. We have that in PE, we have that in ELF as well. Now, the reason that makes thread local storage interesting for purposes of exploring PE, so again, it's just a data directory entry. We'll get you to the metadata about it. We follow that, and we get to this image TLS directory. So the interesting thing here, well, I don't even know if those two first ones really need to be blue and that we care about them. But for normal use of thread local storage where it's just regular data, the start address of raw data is basically saying, oh, and I should say, yeah, as it says here, this is actually a virtual address, not a relative virtual address. So in this field, there's going to be an absolute virtual address. And of course, that means that's going to be subject to relocation. So if you move this around, the linker, if better, have said, okay, for that place right there where there's an absolute virtual address, that better get fixed up later on if you move it in memory. So relocations will have one entry which points at that. But anyways, the point is that's an absolute virtual address which just says for this thread, its data starts here. And then the end address is, again, an absolute virtual address that says for this thread, its data ends here. So rather than using a size, they're using a start and an end. But the very interesting thing, the thing we want to care about here is the address of callbacks. So this is a pointer, and I think it's, yep, it's also an absolute virtual address. It should say that. Maybe annotate your slides there just to be clear. All right, these other two are absolute virtual addresses as well, but this is an absolute address that points at an array of these pointers to TLS callback functions. And just as a miscellaneous thing, there's this field size of 0 fill. This is sort of like for the thread local storage, you can say like, here's the start of my data, here's the end of my data. And you can also do this size of 0 fill, which is like a BSS section tacked onto the end of it. So it's something you can say like, I'm going to allocate this much size. For that, the rest of that stuff, the size of start and end, that's actually space which is allocated in the file. For the size of 0 fill, that's space that you're just going to allocate in virtual memory. So this is what it might look like in whatever it is, bootconfig.exe. You will not find very many things with TLS data associated with them. This was one of the few that I could find. I wrote a hackish program to go search through PE files and just like say, is your data directory entry for, TLS, is that non-zero? And so I just walked through a bunch of files, but it has bugs and I don't really trust it. So this is the only instance that I found in SQL and Windows System 32 that had TLS data associated with it. So we can see there's an absolute virtual address for start of the data, absolute virtual address for the end. So this only has x14 worth of data. And then we didn't care about address of index, but we do care about address of callbacks. So this is an absolute virtual address pointing at a bunch of pointers to callback functions. And so, oh, nice. I think that is ordering, not ordered well. So For each of those structures, so when we go to, oh, I'll show the real thing here. What's going to happen is this address of callbacks is going to point at an array of function pointers, essentially. And each of those function pointers turns out to gets called before the address of entry point. So this is where I said there's the one caveat with respect to, you can set a breakpoint at address of entry point, and theoretically that's going to be the first instructions, which, malware or whatever else is going to be running. But if there exists TLS information, then the OS loader is going to go and find this address of callbacks array, go to that array, and call each of those functions in that array. And then once it's done calling those functions, go back to the address of entry point. So I'm going to pull this up quick. So if you open up pview and go grab bootconfig, bootconfig.exe in C:\Windows System 32, as usual. So if we do that, we'll see, and we expand the .text section, we'll see that there's the image TLS directory, which was pointed to by the data directory entry. And it's saying at absolute virtual address 1011018, that's where we're going to find those callback array. Well, in order to find this in the actual file, what we want to see right now is where in the file is it actually stored. We want to go see those pointers to functions. So if the absolute virtual address is that, then we need to go find the base address and subtract that in order to get a relative virtual address, right? So we go into the optional header, and we find image base, and it's saying it's 10000. So we know we can pretty much just subtract off that first one from the absolute virtual address, and that means this relative virtual address is 11018. So now we have to go in this file to virtual address 11018, right? And really what I'm going to do is I'm literally just going to click around until I see something pretty close to the right range. So I can see there's nothing actually, let's see, this doesn't even cover it. So what I'm going to have to do is I'm going to go back and click on section.txt and literally just scroll down to 11018. So oh, it looks like it's not even, that relative virtual address isn't even in the .text section. So now I'm going to go move on to my .data section. Okay, 11010, and looks like at 18 I have nothing there. So this thing defines some callbacks, but when you go to that virtual address, which should be an array of callbacks, there's nothing there. So it's null terminating. It's saying, oh, sorry, I don't actually have any callbacks. So in order to find something that does have callbacks, we had to go use some example code. So I said TLS itself is rare in regular executables, and things with callbacks is even rarer because you can't even define callbacks with something like Visual Studio. So you can define just regular TLS data, and so I'm just showing this quick. We're again using that declspec thread thing, and again I'm calling that functionally. You can think it's a linker/compiler kind of directive. You can find more about TLS at that link, but the point is mostly what you would just do is declspec thread, and then this is just int. You could call it TLS_I, whatever you want to call it. Point is, there will now be a variable TLS_I, which each thread, when it accesses it, if thread A sets TLSI equal to 1 and thread B sets TLSI equal to 2, they're not going to conflict with each other, right? The thread A is not going to see it equal to 2. So yeah, like it says, there is no way actually within the legitimate linker in order to create these callbacks, so you have to do it manually or use special linkers and stuff like that. So one site you can go to read more about actual using TLS callbacks is this one. So this person is someone who had made a bunch of the articles in Uninformed. And so let's see what he had said here that I wanted to reference. Yep. That's only mostly about regular TLS data. Right, this was basically just saying some hackery that you can use in order to specify TLS callbacks. You're basically just literally defining stuff in your code which organizes data into places that you expect, and therefore then you can like fill in the TLS callback yourself because you very carefully placed function pointers into memory somewhere in your code, and you're like playing tricks on the linker to make sure that the section gets put exactly where you want, stuff like that. But really what we're going to be using for this demo here is we're going to be using the stuff from Ilfac's blog. Oh, no, that's not it, actually. It's this one right here. So we're going to be using this code as our example of TLS callbacks to show that the TLS callback actually gets executed before address of main. Address of entry point, rather. So this is from Hexblog. This is from Ilfac. I shouldn't even try to pronounce his name because I'll get it wrong. And so he just had this very simple code, and he's saying in those comments at the beginning, you know, there's no standard way of creating a function callback, so he actually has to use a special linker in order to link this code in such a way that it eventually fills in that TLS callback function, or TLS callback entry in the TLS information so that it points at the function pointer. Specifically, it's this callback thing. This is what he's putting into his callbacks. And so what he wants is he's going to call message box with hello world, and then he's going to exit process. Now, if an attacker were using TLS callbacks, and if you set a breakpoint on main, the problem is that this callback actually gets executed before main. So it's going to pop something up. It's going to execute code. And so as a reverse engineer or debugger or anything like that, you never want to like be analyzing some malicious code and have it be able to execute code before you start seeing what code is executed, right? So you have to be aware of this notion of TLS callbacks so you can check the executable beforehand. Because otherwise you're going to go in and say, oh, let's see, optional header, address of entry point, I'll set a breakpoint there. And you will fail because they will have executed code which could, you know, mess with your analysis, trick you into thinking that it does something it doesn't do. So follow along on this one. And what we're going to do is, first we're going to use PE view to open up this special TLS crafted executable. So on your desktop under code and then TLS callback, this is basically, you know, in the code thing that you copied from my transfer folder. And under TLS callback, there's a tls.exe. Open that up. And let's see, go to the image TLS directory. And you see the address of callbacks right there. It says 408BB0. Well, I'm just going to guess that 40000 is the base address. And so the RVA is probably 8BB0. So I'm going to click on .text, see if it goes to 8BB0. It does. Yes. Right here. So at 8BB0, right here. Okay, sorry, I'm probably moving a bit fast. All right, does everyone, okay, so yep, first get up your TLS section and you'll see that the absolute virtual address is 408BB0. And then once you go to the .text section and scroll down to what we're assuming is the relative virtual address of 8BB0, you'll see in little endian order what looks sort of like a function pointer because it's 00401618. And so that looks roughly speaking like it could be somewhere within the range 40000. So we think that that's probably going to get executed first, but let's pretend that we don't know about TLS callbacks and we're going to do our normal thing that we do with starting up some malicious code we don't know anything about. We would run WinDebug. So we pull up WinDebug and then we go File, Open Executable. And then again, just navigate to, you know, the desktop code, TLS callback, tls.exe. So what's going to happen is the debugger is going to stop it before it executes any TLS callbacks or the address of entry point. So right now, we're stopped at a breakpoint. This looks like what we normally see. So we're going to go ahead and set a breakpoint on the address of entry point. So back to the PE view. Got to go in there. We look at the NT headers and then optional header. We find the address of entry point. So again, address of entry point is an RVA. It is not an absolute VA. So if we want to set a breakpoint on this thing when it actually loads, we take that RVA and we add it to wherever it's loaded in memory. So 14C8 plus, we're going to go see where it's loaded in memory in WinDebug. It says, okay, I loaded tls.exe at 400000. So I want to do BP for breakpoint, 0x40, and then there's like 14 something. I don't remember. 14C8. 14C8. Right. And so it complains that it can't verify the checksum. That's fine. Right. So we went back to the P headers. We looked at the address of entry point. The address of entry point said, my start of my code starts at RVA 14C8. And so we know that if this is mapped into memory at 40000, we just add 14C8 to that, and that's what we think the initial code should be started at. So now I set that breakpoint. I hit G to run, so to go. And the problem is I can see that it's run code before it hit my breakpoint, right? So the hidden message is the fact that some code executed before my breakpoint, but I set my breakpoint at, the address of entry point. That's the first place that should execute, right? Oh, nice. And we can see that my app init hooked that. I think I haven't taken that out yet. I'll do that next. Oh, that was my reminder. I forgot at the end of the day. For everyone who's doing the remote stuff, I said this at the end of the day in here, but go make sure you change your registry entry to get rid of that app init IAT hook. Otherwise, no one will ever see calc.exe again. Anyways, so the problem here was, if you don't know about TLS, malware can execute code before your breakpoints. The code can literally take away your breakpoint. So we learned in the intermediate x86 class that breakpoints are really just some modification of the code. So the attacker can demodify the code so that you'll never hit your breakpoint. Or they can mess with the debug registers if you're using hardware breakpoints, etc. So now let's try to do this such that we actually can set the breakpoint on the TLS thing so that it won't execute any code before we get a hold of it. So I'm just going to close it. Okay on that. So I closed it. I'm just going to open WinDebug again. I'm just going to open the executable again. tls.exe. And this time, I'm going to set a breakpoint where I think that TLS callback is. So back in the PE view of TLS, I went into the .text section and I scrolled down to 8BB0, and I think this is a callback. I'm going to make this so that it shows it as a D word. So up here at the top, this is byte word D word. So now I'm showing it as a D word, and it does sort of look like it's an array. It's a null terminated array. There's a single function pointer and then a null. All right. So I think this is going to be the absolute virtual address of some callback. So just go ahead and set a breakpoint for 401618. Breakpoint 0x401618. And so now if we're successful when we hit G to let it go, then what should happen is we should stop at some disassemble code, and it should not have popped up that hello world box. All right, so we did stop at some code, and it is in tls.exe. So if I bring up a disassembly window over here, this shows me where I'm at right now. And so basically this is like through here more or less, I think. I believe this is, the bulk of the code which is actually executing. This first call is the call to the popping up the message box, and it doesn't look like it because it's actually calling the import address table. So if I went back to PE view and I looked at, 8 8BD0. I'm guessing that's the import address table entry for message box, which was the original code. It said call message box, then call exit process. So I see two calls here. I'm going to say that's the call message box. I'm going to say that's the call exit process. And it's just calling through the import address table. So let's confirm that. Back in PView, if I go to 8BD0, import address table. Wait, how do I do this? Sure. Okay. 8BD0. The import address table. E0. Well, I could be wrong about that being the import address table, but let's find out by simply stepping into the call. All right, so I'm going to split the screen here. Then I'm going to, right now we're broken at, we stopped at this push EBP. I'm just going to step into, going to check if it needs to jump. It decides it doesn't need to jump. It's going to push some parameters. And then it's going to call into something which I think is message box, but which is, yes. So it's probably compiled a different way so that it jumps through this intermediate table. It's like compiled with intermediate linking. So we can see TLS plus 10A0. I bet that's the import address table. Right, so I end up in message box. So 10A0 is probably message box. So 10A0 is message box A. So this TLS.exe, like it said in the original comment, he used a different linker in order to link it together. So it happened to be a linker which is using this intermediate linking table, which uses this intermediate jump, which then jumps using the data out of the import address table. So a little more complication there, but still the same basic point. All right, so again, right, this is the code we saw. When we went in, looked at the TLS metadata, found the address of some callback in there, then what we got was this function right here, which calls message box and exit process, and we never actually made it to main because it just exits the process. All right, so that was why you need to know about TLS, just so you don't ever get caught by some code. So some packers, for instance, will incorporate a bunch of, so if it's, say, a malicious packer as opposed to just your standard UPX, they'll incorporate a bunch of anti-debug tricks and things like that. And so one of those things they might do is throw in some TLS data so that the packed version of an executable has TLS data so that it jumps to some code and executes some code somewhere that if you don't know about TLS, you don't know that it ever executed that code. So some miscellaneous more stuff you can go read up on your own time. Here's a thing that talks about actually TLS data that then modifies the callbacks table. So like that first function could modify the callback table so that instead of there being a null for the next, for the next thing, terminating it, it could actually add another function into that array of things so that eventually when it returns, the OS calls the next function and that sort of thing. So it can do some hackery. So you could see, oh, well, there's only one function and I only need to look at that. But that function could register another function, which could register another function or things like that. So it can get a bit complicated, and check out this page as well in order to see some more tricks that hackers can throw into stuff. Oh, that's a fail. All right, next thing is, in the data directory, there is a thing for resources. So talk about resources quick. By way of the resource directory, you get, by way of the data directory, you get the resource directory, which has the two things we care about here are the number of named entries, and the number of ID entries. So resources are, generally speaking, used for things like well, I said before, icons, there's some various strings, there's potentially config information. So the resources are sort of organized kind of like a file system, and they're like this little file system that the executable can search that's on the end of the file, and so they can search and look for, this icon or that icon or this or that config file, something like that. So, so we've got this image resource directory, and this is like your header on your little faux file system. And so immediately after this, there's going to be, however many number of named entries, which are going to be some number of data structures of the form that are either going to be interpreted as named entries or ID entries. And each of those structures is called an image resource directory entry. And the point is, each of those can either be identified by a name or an ID. That's why we have named entries and ID entries. And it's basically, there's some number of named entries followed by some number of ID entries. I may be forgetting correctly on that. Yeah, and this is the structure of the resource directory entry, which is highly unioned and structured up and all sorts of good stuff. But it turns out it's actually a little bit easier than it looks. So how it actually works is, so we can see actually there's two big unions. And each of those unions has one D word, two D words, and then a word. So, yeah. Basically, right. So they're just saying, I'm going to give so sorry, this is, for those who haven't seen it before, this is the C syntax for bitwise things. So it's saying this D word, I'm actually going to refer to the top, I believe it's, oh yeah, now I need to think of which way it goes. I believe this is going to be the bottom the bottom 32 bits, or bottom 31 bits, we can call by the name offset2 directory. The top 1 bit is the data is directory. So the point is sort of, for this D word right here, if the top 1 bit of the thing is set to true, then data is directory. And the bottom 31 bits are like some offset2 directory, right? Similar thing going on up there. If the top 1 bit here is true, if it's 1, then name is string, and the bottom 31 bits are an offset to a string. And then, yeah, so this can be either then a name or a D word, or an ID, sorry. Yeah, so that's what this one was basically saying, is that that first D word, if the most significant bit is set, and therefore it starts with an 8, that means the lower 31 bits are just a offset to a string name. And so if the first D word, the most significant bit, is not set, then we treat it as a word-sized ID field. And for the second D word, so again, there's sort of two unions here, where the struct is either, the first D word, which can either be, if this is true, then this is an offset to a string. Otherwise, if it's false, then we just treat that as an ID. So it's either a string or an ID, depending on whether the top bit is 0 or 1. And then for the second D word, if the most significant bit is set, it means the lower 32 bits are an offset to another resource directory. So remember, this is a resource directory entry right here. And if the most significant bit here is set, it's going to point to a resource directory, not a resource directory entry. And if the most significant bit is not set, it means we're finally to some actual data. So there's sort of 4 possible things here. And we'll just jump in and start looking at some resources, and I'll come back to this slide in a second. All right. I'm going to look at, say, Notepad first, for instance. So in PUView, go ahead and open up Notepad. C:\Windows, System 32, Notepad. And if you see there's a .resource section, .rs/rc. And if you expand that, PUView will tell you, okay, well, there's a bunch of these different types of resources, and we don't necessarily know what those are yet. But if we start right here at the very first one, which I believe if we go look at the, I'm going to go confirm this. If I go to the data directory, the first offset RVA should be B0000. So go to here, see the resource entry in the data directory. It says the information about resources starts at RVA B000. So down here, this happens to be B000. So we start out with that image resource directory, as it's saying right here. And so initially there's a bunch of stuff, those are all zeros, as you can see. And then we just have 8 of these, it's calling them ID entries because it's interpreting the fact that they're all ID things. But basically, each of those things below it is one of those 2D word, heavily overloaded sort of structs within unions and stuff like that. So for the first D word, we said if the most significant bit is 1, then I should treat the least significant 31 bits as an offset to a string. Well, we can see in this case, the most significant bit is not 1. Therefore, we instead treat the least significant bits, actually the least significant word, it's not even the full 31 bits. The least significant 16 bits is just an ID. And so this is just an ID which is identifying this particular resource. So the resource can either be named by a name or can be named by an ID. If it's named by a name, the most significant bit is 1. If it's named by an ID, then it's 0. And so this is ID 3, the next one's ID 4, the next one's ID 5. And so these are just saying, these are the IDs or names come first. Secondly, we have that second D word, and it says if the most significant bit is set, then it's a pointer to another directory, and otherwise it's like pointer to the actual data. So the most significant bit here is set, and therefore this is going to be a pointer which is going to be relative to the start of the, sorry, I didn't say that before, relative to the start of the resource information. And that's going to point at another image directory. I'm guessing, yep, there it is right there. So the second thing here, we can see it's B050. That's because we know that there's a image resource directory there because we had went to this first one. And this right here tells me x50 bytes from the start of all my resource information is another image data directory. So basically, what PView has already done for all of these is that they've sort of, walked these things. They call this an ID right there because they can see that, the most significant bit is 0. And so if we go down to, say, let's see if we can find one that has a string for a name. There we go. Here's an example where we can see that there's a image, I believe, image resource directory right there. And then it says, okay, I've got one named entry followed by 3 ID entries. And so the first one is a name, and specifically, the most significant bit is 1. That's why it's set to 8 for the hex nibble. And then this least significant 31 bits is some offset to the name of this particular resource. So I would expect now that if I go, now I'm going to have to just guess and test this. It's either 544 into the file overall or 544 into the resources. But I'm guessing it's 544 into the resources. I should see some string that is the name of this particular resource. So I need to go to B544. Too far. Oh, there we go. So here's like an entire chunk of stuff that's just strings. So B544, that right there is a pointer to the string. It looks like a pointer to a string to me. Let me actually go back here to make sure it's not. Yep. So that's going to be a pointer to a string. So now let's see if I can find that pointer. 4E0010. It could be. Yeah, well, that could be a Unicode string, except I don't see any like double null for null terminator. So if it was a Unicode string, right, there should be 00 at the end, kind of thing. So let's see where this thing's base address is. I'm assuming it's just 40000. Is it? Page base 01. So yep, so I'm not, well, let me see if my slides say, but I don't remember at the moment how to go find the actual string for that resource. Oh, yeah. Okay, yeah, nice. That's why it's confusing. This is, the strings here are delightful because rather than your normal C-style strings, this is like a wide character Pascal type string. So it is like Unicode characters, but it's like Pascal strings in that instead of going for some number of characters and then terminating with a null character, it has up front a size that says my string is this many bytes long, this many Unicode characters long, and therefore then you must read that many Unicode characters. So theoretically, I go back and interpret it now. So up here, there was this. Well, this is a different one. Was I looking at 544? This one right there. So saying at offset 544, there's a Unicode string, but it's like start with the size. How big is the size? All right, I'm not going to get hung up on this because this will just get me into wanting to interpret it, and it'll take forever. Got to keep moving forward. Get to the fun labs. Of course, I say let's walk an example. All right, so anyways, there's only one other point I wanted to make about resources, and this has relevance to Stuxnet again. You can have like full other programs embedded in the resources. And so actually I want to show that at least with Process Explorer, for instance. So Process Explorer is a good example of something that has like an entire other program embedded within it. So if I look at Process Explorer in PView, and I go to the resource section, there's actually, let's see, where is it? Binres. It has these things called Binres resources, which, you know, it chose the name for them, but these are actually full binaries in it. So if I show this in hex view, you can see it starts with an MZ header. Looks like it has a, you know, this program cannot be run from within DOS. And so what these actually these are embedded kernel drivers. So you have Process Explorer.exe, but Process Explorer needs to like run something in the kernel in order to find all the stuff that it looks at. So what it does at runtime is you double-click Process Explorer, it drops out a kernel module, loads that kernel module up, and then the kernel module like communicates information down to it. So, you know, to make it nice and simple for you, they just, you know, bundled everything up so that it has the kernel module together with this exe just embedded. So the thing is so I mean, this is not any knock on resources. I'm just saying that Stuxnet used resources as well as a way of organizing their shell code, like their exploit code, as well as like the kernel modules and stuff like that. So Stuxnet was an interesting example because, right, it was meant to travel along on offline networks, right? So it's traveling through USB. It needs to keep all of its code with it. It isn't like a botnet that can pull down new modules on demand. So it needs to be a self-contained thing. So in order to organize all of its chunks of itself in a well-defined way, it basically just created a resource for each of the things. So if it wants to load up and use some shellcode, it goes to its resources, grabs that resource, and, puts that into a buffer to use as an exploit. If it wants to, take those kernel modules that it loaded into, for hiding files and stuff like that, it would just go into itself, pull out those kernel modules, and stick them into, set them to be loaded up on boot. So resources can be used by malware to just have a nice, easily organized sort of container for any files and data that they want to pull along with them. And it can be used just to make things convenient, like in Process Explorer's case. Right, so that's all I was saying here is that actually what you can do if you, feel like, again, this is a homework sort of problem. If you want, you can take this data starting at, you can write a little program that says starting at, change this over to file offsets, starting at file offset C6198, ending at, whatever, CB at +8. So just dump out that chunk of the file, and then go ahead and throw that into PView, and you can now look at a well-formed kernel module. So you can then, analyze those in turn. All right, getting into the very end miscellaneous thing, there's 2 more things left to go in the PE format. Right, so there's load config, which is, again, data directory. Go to load config. Load config is just this one big structure which has 32-bit versus 64-bit versions. And the 3 things which we care about in here are the security cookie, the SEH handler table, and SEH handler count. So security cookie, this is a VA, this is an absolute virtual address, not a relative virtual address. And this is the location where the stack cookie will be stored in this process's virtual memory space. If this thing is compiled with stack cookies, and so we may or may not have briefly touched on this in the intro x86 class, but when you want to stop, when you want to detect a buffer overflow, what you can do is, Bill, over to the board. Right, so in the intro x86 class, we had done that one buffer overflow example, but I don't remember if I talked too much about stack cookies, because this is for the exploits class for later. But we knew that when we were doing those stack frames, the first thing that the code usually does is push EBP, right? So we always started with that saved EBP, and then we had, locals here. Locals there, saved EBP, and then immediately before saved EBP was the saved EIP, right? So if something calls, some function, the side effect of that call is that it pushes EIP onto the stack, right? Okay. Right, and so in the buffer overflow case, in our simple naive buffer overflow in here, we just had some local buffers here, and we copied enough data that we eventually smashed over this EIP and EBP and stuff like that, right? So in the case of stack cookies, what you do is, I'm trying to think of where exactly it goes, but I feel like it goes here on Windows. You put some random value immediately here before the EBP. So when the code starts, it puts a random value there. And before it executes the return instruction, it goes back and it checks that. And so if you haven't executed the return instruction, actually that's why I think it goes there maybe, but the point is the stack cookie is put somewhere such that you go back and you look for the cookie before you execute return so that you don't pull some corrupted EIP which transfers to attacker code. So the security cookie right here is telling you where in virtual memory you're going to be pulling these random numbers from that you're going to stick into the stack in order to try to detect the presence of these buffer overflows. And then the SEH handler table has to do with, again, there's a type of exploit which, doesn't just stop at the EIP. So it assumes in the presence of these cookies, actually, one type of attack which bypasses this is that it just keeps writing, and then eventually there's these SEH handlers. somewhere else on the stack, like way up farther, somewhere, usually towards the very bottom of the stack, essentially. So if the attacker has a copy such that they could just keep copying like pretty much unlimited data until as far as they want, there's some corruption they can do to these SEH handlers, which eventually will redirect to attacker's code. And so one way in order to counter this is to say, okay, for all these SEH handlers, I am not allowed to transfer to any functions that those specify unless those functions are already written into my binary. So we have a list of function pointers in the binary, and only at the time when it's about to execute an SEH handler, it will not execute that handler unless it's found in this table in the binary. And so that prevents the attacker from overwriting a handler address to point to the attacker's handler address. So the SEH table is an absolute virtual address saying, here's all of the allowed SEH handlers, and the handler count is just saying, how many of those you have to step through. So again, to learn more about SEH overwrites and stuff like that, see Corey's exploit class, which will be taught in the spring term. And the only way to specify that safe SEH in order to prevent those sort of things is by manually setting it in the link options. And again, the GS stack cookie option is here in code generation buffer security check. If you set that to yes, it'll use some heuristics so that in cases where the compiler thinks that there may be the possibility for a buffer overflow, it'll stick in that stack cookie and have that checked before you do a return. All right, final thing in our P format exploration, the data directory entry for security. This turns out to basically just point at a digital certificate. A digital certificate, which is it's the digital signature of the code. And so, as we saw before, there's that DLL characteristics in the optional header. Wait, is it optional header? Yes, optional header. DLL characteristics in the optional header. Is it optional header? Pretty sure it's optional header. I'm going to check that. Like so. And optional header. DLL characteristics, yes? Right, there was that DLL characteristic for force digital signature check. So it's interesting, actually, yeah, I'd want to check this. Process Explorer, which I currently have open, it does have actually a digital certificate embedded in it. So Process Explorer is signed code, but it doesn't have that DLL characteristic saying force a signature check, right? So this will, so if you go onto like a, Vista system or or Win7 system, they may have it set to like, allow, well, the point is they have the option that they can say only allow signed code to run, right? And so in that scenario, only code which has one of these digital certificates attached would be able to run. But by setting that force check, and this, I think this was Reed's point before, right? If I set this characteristic in the DLL characteristic saying, you must check my digital signature before you load me, well, an attacker can, of course, just remove that. If you assume the attacker is modifying code, right, he can remove that force of a check. So a binary telling the operating system, dear operating system, please check my digital signature, that's not particularly strong. It's really about when you're trying to enforce the security there, the operating system has to be saying to all binaries, you must be signed or I will not run you. So, anyways, let's see what RVA the certificate's at. Certificate is at RVA 3FA600. So I'm guessing if I go into the data directory and I go to the security field, where is it? I don't know if there it is. They're calling it certificate table here. I mean, the header files call it the security entry, but so 3FA600, that's just saying I got a digital certificate at this offset. So that's where digital certificates are stored if you ever want to, go through and figure out the format and, be able to extract them and verify them and stuff like that. And the rest of the data directory entries, so we've covered most of them at this point. Right, so we've X'd off pretty much everything that we've covered, including, I'm Xing off the digital certificates one. So there's these couple other, like 3 other ones that I just like tacked on the very, very end of the things. These I don't consider relevant. So all of those are the things I consider relevant for learning about in PE. And so this is just a not fully formed but rough rehash of what's going on with the OS loader at load time. We covered this, piecemeal a bit. But, when you double-click on a PE file, right, you've got an executable. We're going to assume we're double-clicking on an executable. The OS loader is told, I want to load wickedsuiteapp.exe, right? The OS loader goes and finds that file on disk, and it starts reading its PE headers. It says, okay, well, I need to allocate optional header dot size of image worth of memory space, right? So it knows, okay, I got to allocate this much memory space, and then it eventually goes to the section headers, and it says for each of those section headers, start at this size of or pointer to raw data. There's this pointer to raw data field in each of those section headers that says start at this offset in the file, and then there's going to be physical size. There's going to be the size of raw data. There's going to be virtual size. So start at this location, read size of raw data, amount of data, and map that into memory. So for each of those sections, take a chunk of the thing off of disk and map it into memory. And then it reads the permissions on the section, which are asking for, mark this section readable, writable, executable, pageable or not, things like that. So the first thing the OS loader does is it just gets all of that data from disk into memory for every section which is specified in the section header state. All right. Next, what it's going to do is it's going to say, all right, did I have to relocate this from where it wants to be based on its optional header dot image base, right? So if image base was taken already by some other DLL, if you write a DLL, all DLLs are going, if compiled with Visual Studio, are going to have the same default image base. So if you write 2 DLLs and you don't fix up their image base, they're both going to want the same thing. So if you load them both, one of them is going to get the address space, one of them is not. So if the OS loader finds that it had to move a DLL or executable or a kernel module in memory, then it needs to go find the relocation section in the data directory, go to the relocations thing, which is going to be that array of virtual address and then offset from that virtual address. Go to all of those locations and fix up their add in the delta of what you moved this thing by. So there's going to be every single thing in the relocations array is going to be a place where there's a hard-coded address that needs to be fixed. So it needs to go fix those addresses by adding in whatever the delta is. If it's positive hex 1000 or negative hex 1000, whatever it is, it needs to add that to all those locations in the relocations. Next, what it's going to do is it's going to go find the import section, and it's going to say, I need, okay, this module requests the imports from ntdll.dll, user32.dll, whatever. It's going to go in there, and it's going to say, I see that, you have this many DLLs specified. I'm going to go out and get that DLL, but I also have to go get any prerequisites that DLL needs. So if user32.dll imports kernel32.dll, I need to go recurse down and get all of its things. And so that was the hilarity seen with depends.exe, right? So if the OS loader is trying to open something like Notepad, it may start by saying, oh, Notepad, I see you need COMDLG32. It says, oh, COMDLG, I see you need Advanced API 32. And oh, Advanced API, you need this. And so it's going to be potentially recursing down and getting in a bunch of every prerequisite for every module which is a prerequisite of Notepad. Yes, Chris?
At what point would the OS say if it did demand the presence of a certificate?
Are you asking at what point you're asking at one point in the load time process will the OS require a certificate if it's?
Yeah. Well, yeah, approximately.
Well, approximately it would be, I believe it would be between 1 and 2 here, basically. that I think the thing would load it into memory, but it would not actually do anything else until it, like, takes the hash of all the memory that was hashed in order to make the digital certificate check. So I believe it's going to load it into memory, although if it does that, yeah, I'm not sure on that because I don't know whether it's pre-relocations or post-relocations. I believe it would have to be pre because otherwise it would make it more complicated. So I think between 1 and 2.
Okay. 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 I downloaded the article too. I'm just curious because that would seem to at least give some measure of assurance that
Right.
you
That is the point
you're
of the
getting
digital
something.
signature, right? Is that if you're requiring signed code, you don't want to start actually executing or dealing with the code until you verify that the code which you're loading into memory is the same thing that you have a digital signature for. And so, yes, that is where something actually comes into play in terms of trying to enforce, access control and integrity of the code which is running. It's just to make sure someone doesn't change it on disk, basically. So someone can't Trojan that file and modify it on disk. Go
Yeah,
ahead.
Microsoft is still a mystery to me, so
Sure.
I'm learning as I'm going.
And, you said you downloaded the article, but this is a Windows 2000 article, and I don't believe there was signed code in Windows 2000, so that won't talk about it. You just have to Google it.
Yeah, just 2 minutes ago. Yeah, just 2 minutes ago, and I'll Google it in just a sec.
All right, so, right, I said roughly speaking, it maps the thing into memory, fixes up all the relocations if necessary, if the thing had to be moved in memory. Then it's going to recursively go out and get all those imports, and for each of those imports, each of those modules which is imported, it then has to resolve each of the functions by searching the exports table of every module that's requested. And so eventually what it ends up with is that import address table filled in with a bunch of real function pointers. And sort of in concert with this, right, so it may or may not, it depends on whether this executable is bound imports or not bound imports, right? So if it's bound imports, then it would have just went out and sanity checked whether or not this is the right version still. Ah, yes, I broke that apart. That's why. So if it's bound imports, it'll go out and sanity check, and if it's not, then it'll just do what it's going to do in order to resolve all those imported